In continuation with our last lecture, probably we have started continuous time Fourier series. Then I will continue this lecture a bit today, then we'll go to a new topic. Let me share PowerPoint slide. Okay, can you see this slide?
Yes, sir.
Actually, what I will do, I will try to illustrate today how the Fourier series can be applied to an LTI system. Then we will switch to a new topic. Actually, the thing is that at the beginning we discussed that if a signal periodic can be expressed as an infinite sum of complex exponentials, then we know that the output will also be an exponential and they will be related, input and output will be related by a quantity, we call it transfer function. It is the function of frequency. And we discussed it earlier, and that function, okay, just wait a bit, the tab is not working. Okay. What we have seen that the input-output relationship for an LTI system can be, for example, derived with the help of this quantity, Hj omega, we call it transfer function or frequency response. I think you could remember this thing. Now, this concept can only be used when the input can be expressed in the form of complex exponentials, okay? So we have already learned how a continuous and discrete time periodic function can be expressed by using Fourier series exponential. But this example is an application-oriented example how this can be applied to a simple electrical system that we will illustrate today. Now you see that this is a square wave, and you see this is your time origin. With respect to origin, this function is an even function or odd function?
Even.
It is an even function. But when we are using exponential type Fourier series, we usually do not think about our symmetry condition because we have to determine only one Fourier constant xk. Now, if you want to express this square wave into a series of complex exponential, what we need to do, we have to find the Fourier constant xk. So you know from your earlier lecture that Fourier constant xk is simply equal to 1 by t integration over one period xt into e to the power k omega 0 t, where omega 0 is what? The fundamental angular frequency. In our case, what is the period of our signal? You see that if we want to go from this point to that point, it is from minus t by 2 to t by 2, isn't it?
Yes,
So
sir.
this is one period of your signal. If this is one period, then what you need to integrate over one period, the value of xt. We know that here in this case, the amplitude is equal to 1. So the value of xt is equal to 1, omega 0 equal to 2 by t by t. then we can easily integrate it, because within the range from minus t by 2 to t by 2, your signal is existing from minus t0 to t0. So effectively your integration will be from minus t0 to t0 over which your signal exists over one period. Then this integration can be put into this shape. You see that if we have our thing there, if your k0 equal to 0, then this expression cannot be evaluated. The reason is that at k0 equal to 0, it becomes undefined. So by using Euler identity, you can easily express this quantity into a sinusoidal function, something like this. Then this will be the value expression for our xk. And what is the value of xk at k equal to 0? Because this is not applicable for k equal to 0. How to find it? For k equal to 0? Don't you know your L Hospital's rule there?
Yes, sir. We will use that rule.
Then if we apply your L Hospital's rule there, then what will happen? Because we are changing the value k, then you differentiate your numerator with respect to k. Then it will be equal to what? 2 omega 0 t0 into cosine k omega 0 t0, and your denominator will be equal to t omega 0. Then you put your k equal to 0 there. Then it will be equal to what?
2.
It will be equal to 2. So this is what the, actually this is nothing but the average value of your signal. Is it not the average value for k equal to 0? For k equal to 0, you are getting the constant term x0. And for if your k equal to 0 in this expression, then this integral will be 1 by t, integration from minus t by 2 to t by 2. Minus t, this is not equal to 2. Is it 2? This should be equal to 2 t0 divided by t at k equal to 0. Okay? Yes. So your integration from minus t by 2 to xt dt for k equal to 0. Is it not the average value of your signal over one period?
Yes, sir.
Then you can easily verify that your average value would be equal to 1 by t integration from minus t0 to t0. The value of your signal is 1 dt, and that is equal to 2 t0 divided by t. Anybody can say this, okay? So this is what the average value of your signal. In this way, once our Fourier constants are determined, that will tell you that which harmonics are there in your signal. So it's ranging from k equal to minus infinity to infinity. And this type of function is very similar to a mathematical function, is called sampling function. Have you heard about sampling function earlier? The nature of the function is something like this: sin x divided by x.
Yes, sir.
So this function looks like this. Okay, so you see that your Fourier constant is actually has a maximum value at k equal to 0, and we'll have values for k equal to minus and plus in the k plane, and that will looks like a damping sinusoid. Okay, so all the things we have already discussed. So this is what our final expression for our signal if we place or replace our omega 0 by 2 pi by t. Now you can, okay, this is a discrete function, okay? It is not a continuous function because your k is discrete. So you can easily plot a stem figure in your map by your MATLAB. We'll have a maximum value here, another stem can be there, another stem can be there, another stem can be there, something like this, okay? It will look like this, okay, in either way. It will have 0. You can easily find where you sign for this function can be 0. So this Fourier constant will have this shape. Now, if this Fourier function is present from this Fourier coefficient, this is nothing but the amplitude of our harmonics for a particular value of k. So if we know the amplitude of this quantity, then that our signal is actually expressed as xt equal to sum k equal to minus infinity to infinity xk, the Fourier constant, the reconstruction equation or synthesis equation, e to the power j omega 0 kt. This is what our signal now. Then if this signal is given as the input, then we will get an output. That output will also be equal to what? A sum k equal to minus infinity to infinity. Then we will have our A's. A's will not exist for our frequencies, although theoretically we can determine Hg omega. But once that Hg omega is determined from input-output relationship or from circuit theory, I have illustrated for the case of an RC circuit earlier. Then generally if your omega is continuous, then this will be a continuous function of omega. But if your omega is discrete, then it becomes a discrete function. Okay, in our case, not all frequencies are existing. Only this frequency, this value is existing. So the corresponding value of H will be equal to H at that particular frequency, Hg omega. Okay, then e to the power j omega 0 t. Okay, your signal will be there, but our signal is what? Our signal is, this is your transfer function. Then your signal is this. It is equal to xk e to the power j omega 0 kt. So this is what your output. Then we can easily see that your output yt is also looking like a Fourier series. The new Fourier constant would be equal to hj k omega 0 multiplied by xk. So once your h is available, then we can calculate the output yt by using this another new Fourier sum. Now the thing is that for any harmonic, the amplitude of your output can be calculated as the amplitude of our output for a particular harmonic would be equal to hj k omega 0 multiplied by xk. The amplitude of this thing, so we can consider this as say y, say k. So your yk is the new Fourier constants for your output. And the amplitude of your output for a particular value of k will be the amplitude of y for that particular value of k. Let us illustrate this by using an example. Then this will be the generalized thing, okay, for any circuit or system. If your transfer function is available, then we can calculate the output of our system in this way. So the functional description is there, how a sampling function is defined. So this is left to you to be understood. Another version of the sampling function is called sinc function. This is defined in this way, just by changing the variable x to pi by x. This function is needed in many of our communication systems. Okay, plot of this function. Okay, you can easily see that it will like a damping sinusoid as a maximum value equal to 1 at the variable x equal to 0. And it will have main lobe and some side lobes are also there with gradually decreasing amplitude. So the expression xk is expressed in the form of sinc function by using the earlier slide. Then in the form of sinc function, it can be expressed in this way. Now the illustration, okay, although I have already discussed the thing, then this would be our input-output relationship in general for a single output and single input system if the transfer function is available. Now, a new Fourier constant will be with us then. That for a new Fourier constant will be equal to this. Okay, this is the transfer function at the harmonic frequency multiplied by the corresponding Fourier constants of the input. Now, this is usable only when your transfer function is available. Okay, so in our earlier example of an RC circuit, okay, how can we find the transfer function of the RT circuit? You simply replace your circuit into frequency domain by replacing this was our output YT, this is C, this is R, this is XT, okay? When you transfer this circuit into frequency domain, then your input will be, say, there, R will remain unchanged. Then your C can be replaced by what? 1 divided by j omega C. Then you can easily find that if we take output across the capacitor, then Hj omega would be equal to what? 1 divided by j omega C divided by R plus 1 by j omega C. And this is what your transfer function. By using simple circuit theory, you can easily determine this transfer function. So if this transfer function is available, then we can reshape this transfer function into this form. So this is very applicable for all continuous frequency omega. Then in our case, not all frequencies are existing. This is what that term is existing, okay? An integer multiple of omega 0. Thus the corresponding value of your Hj omega would be equal to simply replace your omega, continuous omega by omega 0 k. Then this will be our transfer function for a particular harmonic k. Then if this is k, then we multiply this function, we multiply this quantity, okay, by changing the value omega 0 equal to twice pi divided by t. In this example, they considered that your RC equal to say 0.1 second, the time constant. Your omega 0 is considered as twice pi, t0 divided by t equal to 1 by 4. Using these values, your yk can be determined in this way. This is what your h j omega k, and this is the value of your Fourier constant xk. Then this is your new yk. Then your output yt would be equal to sum of your this term. Now, if you want to use computer or by hand calculator to solve this problem, then we cannot go for example from k equal to minus infinity to infinity. What we need to do, we have to sum for a finite numbers of terms. You can easily see that if we plot our xk and both this yk, that is, if we plot the magnitude of yk, are not the magnitude is a decreasing function of k?
Yes, sir.
Because you see that your Fourier constant of your signal xk is a decreasing function of k, and you have already seen there. And the transfer function, magnitude of the transfer function is also a decreasing function of k. So as a result, the multiplication yk is equal to xk multiplied by h j omega 0 k is also a decreasing function of k. As a result, we can always truncate this series by using some finite numbers of terms. You can experiment it by your own using your MATLAB. In your book, there exist some plots for different values of ranges of k, and you can easily observe that how your signal output is going. Okay, what will be in general, what will be the shape of the output? Can you tell me? Because if your input is a pulse like something, then your output would be equal to what? Because your capacitor is getting charged, and if it is getting charged, then again output is not there, it will begin to discharge, isn't it?
Yes, sir.
So your output will be looking like this. Now this will happen theoretically if we add infinite numbers of harmonics there. But you will see that if we truncate to a finite numbers of terms, although it will not be looking like exactly this, it will be something like this, okay? It will be an approximate function, something like this. And it is fairly accurate to proceed with our further calculation. So you can easily observe how the harmonic number affects your output by experimenting it using your MATLAB. It is simply you plot the magnitude of yk, and that will tell you how your signal is. Then you add this for k. You can start from k equal to say from -5 to 5. Then you gradually increase the value of k and look how your output is approaching to the exact output. Okay, after how many minutes? 30 minutes, only 35 students joined. I will not be giving their percentage today, okay? Your percentage will be given now. Because your online class, you guys are abusing the technology and also undermining, for example, the effort of your teachers. So you tell your peers, those who are poking into there to admit, I will not admit them, okay, for today. If they can come into the class within 10 minutes, only when they will get admit, otherwise not, from the next class. One or two might have problem, but 50% of the student cannot have the problem, okay? So this is what the case, okay? If we have our circuit or system given, an input is given, your step will be what? You express your periodic input into Fourier series, then you determine your transfer function, then you multiply your transfer function with what? Multiply your transfer function with the Fourier constants of your input, that will give you a new Fourier constant of your output. Then you sum this Fourier constant with the multiplication of this term, e to the power j k omega 0 t, then you will get your output. And you can easily truncate your sum to a finite numbers of Fourier terms. The reason is that your yk will be a decreasing function of what? Fourier harmonic. So this is what the thing I have illustrated. So your square wave is there, your output will be in fact something like this, but try to observe that how your output will behave for finite numbers of k. Now this is an example corresponding to your what do you call electronic circuit. Do you know the switching mode power supply? That means we can generate, for example, an AC signal by using a DC?
Yes, sir.
Okay, then you try to revisit this example with the help of your power electronics knowledge. You know this thing. This is the Fourier transformation from your exponential form to trigonometric form. You try to look at it. Now I will be illustrating few things that sometimes some symmetry condition can help to reduce, for example, our labor if we want to use our the trigonometric Fourier series to analyze your periodic functions. For example, what is your idea? Okay, initially consider this black figure. This curve is even or odd? This one?
Even.
It is an even function of okay, it is an even function. Now if we, for example, shift the horizontal axis upward by a value equal to say a, then what will happen? Say this amplitude is twice a and this is a, then what will happen? This part will be coming to the negative side, isn't it? Then how your signal will look like? Your new signal will be, okay, you can consider plotting it in this way. Something like this, isn't it?
Yes, sir.
Yes, sir.
It is now the symmetry condition is changed. The evenness or oddness of your signal is same, or it is changed to some other symmetry.
So it's still even.
It is still even, isn't it? But what change is there by shifting the horizontal axis?
The DC value is.
The DC value is changed. Okay, that is what the thing, you know, this thing. Then we can easily find that how much DC value is changed if we shift the signal in the horizontal axis. But if we shift the signal, for example, if we shift the vertical axis in this direction, what will happen? Say we are bringing the vertical axis in this new location. We want to bring our vertical axis to this location here. Then what will happen? Your signal is something like this, okay? It is going in this way, again, something like this, isn't it? That means your signal symmetry is changed from even to odd, isn't it?
Yes, sir.
This is very similar to something like this. If we have a cosinusoidal wave, something like this, if we shift the axis, okay, say this axis cuts at 0 axis at this point, okay. If we shift this vertical axis to this location, then what will happen? Then your sine curve become a cosine curve become a sine curve, isn't it? That means a 90-degree phase shift occurred. Actually, this is what the thing. If we shift the vertical axis, it will change the symmetry condition of your signal and eventually create some phase shift in your signal, okay? But if we shift the horizontal axis, that will change the average value of our signal. This is the shifting property. When we will be discussing about properties of the Fourier representation, we will again revisit the thing. Let us finish our general discussion first. Okay, so this is what our Fourier series all about. Although we have revisited the thing in mathematics, you have already the thing with you. But we will again be discussing about some practical applications of Fourier series later, okay, after finishing our mathematical background. So now we will be discussing about another class of time property that is called non-periodic type. Okay, that means if your signal is not periodic. Okay, another issue that I need to discuss at this point, although those things, okay, let me share the whiteboard just to give an idea about it. Okay, what we have seen that our Fourier constant xk for the square wave has this property, okay? That, okay, let me plot it in a continuous manner with the assumption that only the discrete values will be existing, okay? Only the discrete values will be existing for k. Okay, this is your k-axis. Okay, you can easily see that in our sine term, what was there? Sine omega 0, say t into k, something like this. Can you tell me when this quantity will be equal to 0? When, for example, omega 0 tk would be equal to 0. Can you tell what would be the value of k? When this becomes what? And plus minus integer multiple of pi, isn't it?
Yes, sir.
Yes, sir.
Then what will be the value of k? Your k would be equal to plus minus n pi divided by what? Omega 0,
T.
say t. Some other factors are there. Okay, forget about the, consider the t first, okay? Consider this is not the case. Then thing will not change that much. Your omega 0, okay, no. Let us see the exact expression. What is the exact expression? It was equal to it was equal to 2 sine k 2 pi t 0 divided by t divided by k 2 pi. Okay, when it will be equal to 0, when k into 2 pi multiplied by t0 divided by t is equal to, say, plus minus n pi, isn't it? Then those zeros will be appearing. Then can we find the value of k when the 0 will be appearing? Then k equal to what? Plus minus n pi divided by 2 pi into t divided by t0, isn't it?
Yes, sir.
These things are there. So your k equal to n into t divided by 2t0 or something like this. Okay, from this expression, okay, so these are the values of k. For example, say at n equal to 0, this is what that value. At n equal to 1, this is this value. And for n equal to minus 1, the value of k is this. Now the thing is that you see, if you t0, it is that value of k is inversely proportional to t0, isn't it?
Yes, sir.
If your t0, for example, is wider, then what will happen? This curve will be narrower, isn't it? That means this curve will be taking in this shape. But if your t0 is smaller, then this become wider, isn't it? So what does it mean? It means that in the frequency domain, if your pulse duration is smaller, then what will happen? You see that in this curve, you see the maximum, the value of your k is contained within the main lobe. That means the most of the energy will be contained in the main lobe. So if we have our signal duration that is very small, that will require what? Larger bandwidth to accommodate all the energy. But if the signal is duration is longer, it will take lesser bandwidth. Okay, for this reason, for high speed signal lines where your pulse duration is very small, in this case, what will happen? You need longer bandwidth, or bandwidth should be larger, otherwise your signal cannot be transmitted. Okay, that is very important issue in designing our communication channel or any system that processes high speed signal. Now we have our another class of signal where your periodicity is not there. That means your signal is aperiodic type. So you have your two types of aperiodic signal. One is discrete time, another is continuous time. So in this book, they dealt with discrete time. So we will be going with discrete time. So your Fourier transform, here in this case, the Fourier series is not applicable. We will be using Fourier transform. So in the Fourier transform, this is what the transform technique. Okay, it is bidirectional. So if we have an xn, then it can be transferred to frequency domain by a quantity that is x e to the power j capital omega. When this function is appearing, we have to understand that this is the Fourier transform of a discrete time aperiodic signal. And this capital omega represent the continuous frequency in your discrete time frequency domain. Now, how the thing will be there? If we have an xn that is aperiodic, then we can evaluate the sum from n equal to minus infinity to infinity xn e to the power j capital omega n. This will transform our aperiodic signal into frequency domain, and this is what that value x e to the power j omega. So the Fourier transform of a discrete time signal aperiodic xn is defined as this by this equation. So this is what our analysis equation. Then if x e to the power j omega is available to us, then we can reconstruct our signal by using this sum. So this is our synthesis equation. These two equations are called transform pairs, and they will be appearing in pair. Okay, only one transformation is not enough. We have to move if we can go into the frequency domain by using forward transformation, then we can again come back to the time domain by inverse transformation. So this equation is actually inverse Fourier transform, and this equation is Fourier transform. Now, why this integral is omega limit is from minus pi by 2 pi by 2? This is there because this term signifies that if we have e to the power j omega n there, then what will happen if we want to, or if we go there, then what will happen? You see that this term has a property, unlike the continuous time signal, that if we increase the value of, say, omega by twice pi into n, you will see that this will be equal to e to the power j omega phi n. This means that this sum actually will give you, this quantity will be periodic, and if this is the periodic thing, then only that one cycle of your period is enough to reconstruct this signal. So you integrate, you need only to go from minus pi by 2 to pi by pi minus pi to pi just to grab one cycle of our Fourier transform. That is enough to reconstruct the signal. In the case of Fourier series, we have seen that the period of xk is also equal to the period of xn. So we have only n numbers of distinct values of xk to reconstruct the signal. Let us illustrate the thing by using some examples. Okay, consider a sequence xn is equal to alpha to the power n un. From this point, okay, using this example, many of the important issues will be resolved. So, try to listen it carefully. Okay, this is our signal. Xn is equal to alpha to the power n un. Is this a periodic signal or aperiodic?
Period.
Non-periodic?
Non-periodic.
It is non-periodic. Okay, this signal is usable only when your alpha value will be less than 1. Okay. If your alpha is greater than 1, then in course of time this signal will be unbounded. Okay, so this is a signal. If we want to plot it for alpha value less than 1, it will be something like this, like a decreasing function of n, isn't it?
Yes, sir.
And un as the magnitude is equal to
1.
un as the magnitude equal to 1 for n equal to
N greater than equal 0.
n greater than equal 0. Good. So with this thing, let us start with our forward transformation. Okay, we have to convert it into what? Fourier transform. Okay. So our generalized Fourier transform equation is Fourier transform of a periodic function is something like this, is equal to sum n equals minus infinity to infinity, what? Xn e to the power minus j capital omega n. Okay, this is what our general equation. So in our case, your signal exists from n equal to where to where?
0 to infinity.
N equal to 0 to infinity, yes. Because your un signifies that we have our signal from n equal to 0 to infinity. So your sum will be from 0 to infinity. And within this region, our signal is alpha to the power n. And we know for each value of n within that region, un has the value equal to 1, isn't it? So multiplication of un in this equation will not change the signal. For this region, we can easily write that within our within our region from n equal to 0 to infinity, un has the value equal to 1 for n equal to 0 to infinity, isn't it? So the 1 is there. Now, if we want to evaluate this sum, you know this thing, how can we write this sum, okay? This is equal to what? This can be written as e to the power n equal to 0 to infinity alpha e to the power minus j capital omega to the power n, isn't it?
Yes, sir.
And that quantity can be thought as another constant. So the sum is something like this, isn't it? This, if we want to sum it, say n equal to 0 to infinity, say a to the power n is equal to what? It is equal to 1 divided by 1 minus a, isn't it?
Yes, sir.
So if this is the thing, in our case, our a equal to what? Alpha e to the power minus j omega. So this is what you sum. And alpha magnitude must be less than 1. Otherwise, your signal is unbounded, okay? Now you tell me your x j omega, okay? By using this example, we can easily see that our x j omega, is it real or complex?
Complex.
Yes, it is complex. So it has a real part and an imaginary part. Okay, we can rewrite your x j omega in this way by using Euler identity. Then you can easily find that the magnitude equal to what? X j omega magnitude equal to 1 divided by
1 minus
1 minus alpha cos omega square plus
alpha sine
alpha square sine square omega, isn't it?
Yes, sir.
Then you can easily write this equation in this form: 1 divided by 1 minus 2 alpha into cosine omega plus alpha square in cosine square omega plus alpha square sine square omega square root, isn't it?
Yes, sir.
Then your alpha square and this alpha square would be equal to 1. So it will be equal to what? A square root of 1 minus alpha square minus 2 alpha into sine.
1 plus alpha square, I think it is.
1 plus alpha square, yes. So in this way, you can easily find the odd value, the real, okay? That means the magnitude. If your magnitude is available, then you can calculate the phase angle also, okay? So in general, then a plot will be there that will be plotted. If your x magnitude is plotted with respect to omega, and you see that in the case of Fourier series, we calculated the Fourier constants for discrete values of Fourier harmonic number k. So only discrete frequencies exist. But here in our case, it is the continuous function of the frequency capital omega. So we can have a plot that will illustrate the variation of magnitude of x e to the power j omega with respect to omega, that we call magnitude spectrum. And if we plot the angle of e to the power j omega with respect to omega, we call it phase spectrum. So both your phase and magnitude will be needed to reconstruct our signal. Okay, this figure illustrates the magnitude and phase spectrum for different values of alpha. Okay, for alpha is equal to 2.5, you see that your figure is something like this. Is it not periodic with period equal to twice pi?
Yes, sir.
It is periodic with period equal to twice pi. And if we change the value of alpha to a larger value, say alpha equal to 0.9, then the figure will be looking like this, okay. Now, how about the angle? We can easily calculate the angle also. Your angle spectrum is also periodic with respect to omega, okay? In order to reconstruct our signal, we need the value of x e to the power j omega from where to where? For omega equal to minus pi to pi, or from 0 to twice pi. Okay, this is enough to reconstruct our signal. In this way, we can transfer our aperiodic signal from a time domain to frequency domain and vice versa. Let us proceed with other issues. Then this problem, e to the power this and this. Can you tell me, can you find the solution of this problem? Here in this case, what is this?
The signal exists only for negative values of n.
That means for negative values of n. So our sum will be what then?
Minus infinity to 0.
From minus infinity to 0. Can we change the variable just to reverse it from 0 to infinity?
Yes, sir. We can use.
Change from n to m, minus n to n.
Yes, sir.
So in this way, try to solve this problem and verify this result. Okay.
Yes, sir.
And this type of problem will be there in your class test also. We'll be taking a class test on the 14th, inshallah, with very tiny type problem, MCQ type and simple calculative type by using IIT LMS. I will let you know when I will set it. Actually, I am busy with many other things and getting cannot afford time to do that yet. Inshallah, I will do it in this weekend. So your problem will be very simple. And as you know that we cannot give the exact reproduction of the problem there, but something will be there that you can solve it very easily. So try to solve some problem to get accustomed to this equation. Okay, another example is there in your book. This is also very interesting. Let me show it to you. Okay, consider this signal. Your signal xn is equal to 1 for magnitude of n is less than equal to m, and it is 0 for magnitude greater than m. Can you imagine what is the shape of your problem signal? Is it not a magnitude of m less than equal to m means what? That means this is for n is for n from minus m to
M.
Okay. That means you have a signal, say this value is from minus m and this value is say m. And this is discrete term, of course. Then what will happen? Your signal is something like this, okay? Is it not your signal? This is your xn. Okay? And this axis is n. So is it not a pulse, rectangular pulse with duration equal to how many samples are there?
Twice m.
No, twice m plus
Plus
at
1.
Twice m plus 1. So your total sample is twice m plus 1. Numbers of samples are there. Now your thing is very simple. Okay, if you want to Fourier transform it, just your amplitude equal to 1 and it is e to the power minus j omega n, the general formula. Your sum will be from minus m to m. But if we have this type of sum, sometimes we can evaluate it, but in other cases you can change the variable to use the general formula of your sum. Can we change the variable in this way so that your sum can be done from 0 to a certain value?
Yes, sir.
If we replace, for example, our if this replacement is made, then you can easily see that our sum can be done in this way, okay? From m equal to 0 to twice m. If we have this sum with us, say m equal to 0 to twice m, and some a is there, say a m is there, then this sum equal to what? 1 minus a to the power twice m plus 1 divided by 1 minus a. Isn't it?
Sir.
Okay. Then this transformation is actually aimed at to use this closed form. Okay. So when we replace this thing, then your replacement is this. Now the thing is that when we replace our m, this thing, then your n would be equal to m minus capital M, isn't it?
Yes.
Then we have a term there, e to the power minus j omega n, and that will be equal to what? E to the power minus j omega
M minus.
m minus capital M, isn't it? And here m is the variable, capital M is not variable. Then you can separate this term e to the power j omega capital M into e to the power minus j omega m. Okay. So your this is taken out of your sum. Then we can easily evaluate the sum into this form. Here in this case, our a equal to what? E to the power minus j
Omega.
capital omega. Yes. So we can easily evaluate the sum, and you can see that at omega equal to 0, this sum will not exist. You can easily express this sum into use sinusoidal form. Can we do that? In here you see you have, because we have seen this type of equation earlier in the case of Fourier series also. 1 minus e to the power minus j omega twice m plus 1. Okay. Can we write this thing in this way, that a product of two exponentials?
Yes, sir.
For example, if we have a term e to the power minus j say theta, we can easily write it at e to the power minus j theta by 2 into e to the power minus j theta by 2. Can we write this?
Yes, sir.
Similarly, if we have a term 1 can be written as e to the power minus j theta by 2 into e to the power plus j theta by 2. Can we write this?
Yes, sir. We can.
Then if we have our say 1 minus e to the power say minus j theta, that can be written as e to the power minus j theta divided by 2 common e to the power j theta by 2 minus e to the power minus j theta by 2. Can we write this?
Yes, sir.
Then what is this? Can we we can easily convert this quantity into Euler identity to cosine or sine, isn't it? So this expression can be again by using this simple mathematics. We can easily convert this x Fourier transform into equivalent sine or cosine forms. Okay, so this transformation is done here. Here is this thing, okay? Both your numerator and denominator can be transformed into this thing. Okay, if you want to plot it, you see that is the periodic function of omega. If you want to plot it, you will see that it has a maximum value at what? For the lowest value of omega, at which it will be maximum equal to omega equal to 0. At omega equal to 0, its value would be equal to what? At omega equal to 0, the value will be equal to at omega equal to 0, what will be the value? This value at omega equal to 0 can be determined by Euler identity, isn't it? By
Yes,
using L'Hospital's rule.
Yes, sir.
Yes, sir.
You differentiate it with respect to capital omega. It will be equal to twice m plus 1 divided by 2 divided by half, isn't it, is equal to at k at omega equal to 0, and that will be equal to what? Twice m plus 1. So the maximum value of your Fourier transform will be occurring at omega equal to 0 and at omega equal to multiple of twice pi, isn't it?
Yes, sir.
Because after twice pi, the same thing will be appearing. So this is what the maximum value they are appearing, okay? Then from pi to pi, it will constitute a cycle in your Fourier transform, okay? So, okay, from this thing, what you can understand that at the receiving end, for example, after processing, we can record, if we know the Fourier values from Fourier transform values from minus pi by 2 to pi by 2, we can reconstruct the signal. But you see that theoretically, although we can integrate from minus pi by 2 to pi by 2, but you see that this 0 is occurring at this point, okay? Twice pi, okay, you can easily find that your xj omega will be 0 at what? If omega into twice m plus 1 divided by 2 equal to plus minus n pi, isn't it?
Yes, sir.
Where n is an integer value, okay, you can consider it p pi, because in order to not get confused with our p pi. So for a minimum value p equal to 1, so this will be equal to plus minus pi. That this is what the first 0 point, okay? The first 0 is occurring at what frequency? Omega equal to what? You can easily
2
find
pi by 2m plus 1.
2 pi divided by 2m plus 1. Is it not this thing? 2 pi by in plus side, another will be at the minus side, okay? So within this frequency range, you see that most of your energy of your signal is contained, isn't it? So even if we integrate or take the Fourier inverse within this interval, not going to minus pi by 2 pi by 2, still we can reconstruct our signal faithfully. The reason is that most of your signal is there. Now we will show later that if we transform a signal from one domain to another domain, energy must be conserved. You understand the thing? Probably in your first year, when I talked about something about RMS value or something like this, at that time we discussed a bit about it. That when we what is your for example understanding, intuitive understanding, that if we have a signal xt, it has an energy. That energy we calculated for by using this equation x square t dt, isn't it?
Yes.
Then if we, for example, express this signal into another form, say k equal to minus infinity to infinity xk e to the power, say j omega 0 kt for the case of continuous time. Now tell me, if we want to square it, and this is a complex quantity that will not contribute to our energy, isn't it? Will it contribute to our energy?
No, sir.
Because the magnitude of this quantity is always equal to 1. Then this is what the thing, the magnitude of xk square, that will contribute to the energy, isn't it? So the Fourier constant that we determined earlier, the square of the Fourier constants also related to energy. And if we express a signal from one form to another, that means after transformation, the energy of your signal must be conserved, isn't it?
Yes,
The energy must be same. This is an important theory, is called Parseval's identity. We will discuss more about it afterwards, okay? But in this case, you can, using this energy conservation, you see that if we integrate, for example, from minus pi by 2 to pi by 2, as we can reconstruct our signal, then total energy of the signal can also be extracted. But that will have a bandwidth requirement, but we know that our magnitude of x square, magnitude of x e to the power j omega square is also a measure of energy. So if it is the measure of energy, then you can easily see that as this is the main lobe, your main lobe has a larger area than your side lobes. Okay, your side lobes are diminishing. As a result, most of the energy is contained where? In the main lobe, isn't it? most of the energy is contained where?
At 0, omega equal to 0.
In the main lobe, okay? In this area, in the main lobe, okay? So if we integrate, for example, from minus twice pi divided by twice m plus 1 to plus twice pi divided by twice m plus 1, then we can have our total energy there, almost total energy. As a result, some energy will be there in terms of sub loss or something like this. Still the efficiency of your system will be higher, okay? So this cannot be understood in the time domain. For this reason, actually, we need Fourier mathematics to know the frequency content of your signal, as well as in which frequency range most of the energy of your signal is contained. Then that will help us to design a real system. So this is what your Fourier transform of a single pulse. Okay, now let us go in the reverse way. From this point, some interesting thing will be occurring, okay? That means, okay, so let me conclude it at this point. Then we'll be discussing things, this thing. Okay. One thing is that for a periodic signal, we have to use Fourier transform, okay? Your Fourier transform has an forward transformation and an inverse transformation. Inverse transformation will bring back your signal into the time domain, and your forward transformation will transfer your signal to the frequency domain. Your frequency Fourier transform of an aperiodic signal that is discrete time is a continuous function of capital omega, and it is periodic. We need only one period of your Fourier transform to reconstruct our signal. And we have seen that for the case of a rectangular pulse, we have seen that the Fourier transform of the rectangular pulse is become a sinc function or sinusoidal function with maximum value occurring at omega equal to 0 or multiple of twice pi. So this is one important observation you have to understand. That means if we have a discrete pulse, again I am rewriting it, if we have a discrete pulse, okay, something like this, then your Fourier transform will be something like this, okay? That means a sinc time function in the frequency domain. This axis is capital omega. This is your n. That means a pulse in your time domain, of course discrete, is generating a Fourier transform that is a sinc function like function in the frequency domain. And most of the energy is contained within the main lobe. Okay. Now with this thing, let us start with the inverse problem. Consider that we have a pulse in the frequency domain. A frequency domain's pulse can be defined in this way. That we have a Fourier transform of a function. That Fourier transform has this thing, okay? That means the value of your Fourier transform magnitude is equal to 1 if your omega is from minus w to plus w. And it is 0 between minus pi to pi. And we know that this thing will be appearing periodically. Only one period is shown here. And that is enough to reconstruct our signal. So this is what our Fourier transform of a particular, and this is for whenever, for example, this is appearing, you have to consider that the resulting signal will be xn, not xt, the discrete time. If you want to find the discrete time signal corresponding to this transform, then what you need to do, we have to evaluate the integral. We know that your xn would be equal to 1 divided by twice pi integration from minus pi to pi x e to the power j capital omega e to the power j capital omega n d capital omega. That integration we have to evaluate. So this integration is done there. we need not to go from minus pi to pi, because your spectrum exists from capital minus capital W to W, so W to W, and we have this thing. And you can easily identify that this is also a sinc function like function in the Xn, okay? That you need to remember. If we have a pulse, continuous pulse in our frequency domain, that will generate a time domain signal that is very similar to a sinc function, but discrete. And similarly, if we have a discrete pulse in your time domain, that will generate a continuous sinc function in the frequency domain. So with this thing, I need to conclude my today's lecture. But I am sorry to say that I could not allow the others to try to make them understand that their class is important. So from the next class, I want that everyone should join in my class within 5 minutes. So that's all from my part. Thank you.
Sir,
Yes.